Hello viewers, welcome to MAGESH classes. In this presentation we are going to deal about DIEL ALDER reaction. The DIEL ALDER reaction, it is a type of cycloaddition reactions and it is occurs between the conjugated diene and alkene or alkyne. It is a dienophile. In this type of DIEL ALDER reaction there is a loss of two pi bonds and formation of two sigma bonds. So in the pictorial we can see that the two pi bonds and here the two sigma bonds are formed. So totally three pi bonds are there. So collectively two pi bonds lost. So in the product it has only one pi bond and there is a two sigma bonds between the dienophile and the diene. Let us consider one question. It is a TRB question. Teacher Record Board Tamil Nadu. Here the couple of questions. One is a DIEL ALDER reaction between 1,3-butadiene and ethylene. So reaction between DIEL ALDER reaction and the adductant catalytic hydrogenation. So catalytic hydrogenation means so all the double bond present in the compound is converted into single. So merely in DIEL ALDER reaction the product is a cyclic adduct. We know very well. And by losing 1,3-butadiene consists of two double bond and ethylene consists of one double bond. Totally three double bond. Losing two double bonds you get one double bond. So this is a product. And catalytic hydrogenation means it is hydrogenated to give the cyclohexene. So B is the product. Okay. Then it is the 4+2 cycloaddition reaction. Why it is called 4+2 addition reactions? In butadiene it consists of 4 pi electrons and in alkene, ethylene or alkyne there is a 2 pi electrons. So cycloaddition involves 4 by suprafacial and suprafacial. That is the overlapping of the orbital is suprafacial. So there is anterofacial and suprafacial, that is overlapping on the same plane of the 4 pi s orbital of the butadiene and the 2 pi orbital of the ethylene. So by means of FMO approach, that is frontal molecular orbital approach, one component is in the HOMO, electron rich, and another one is the LUMO. So it is highest occupied molecular orbital, so it is electron rich, and a LUMO, lowest unoccupied molecular orbital, it is electron poor component. Okay, and this DIEL ALDER reaction is thermally allowed. So photochemically it is forbidden one. So this based on the mechanism concept. So regarding DIEL ALDER reaction, it is a cycloaddition 4+2 and thermally allowed. The losing of two pi bonds and the gain of two sigma bonds. Okay. Next one is the nature of the diene involved in the DIEL ALDER reaction. Generally, diene is a electron-rich species. Okay, and some other electron-releasing groups are present in the diene. It may be reactive in greater extent. So this is a butadiene. This butadiene is an electron-rich compound due to the presence of 2 pi electron, and it is a HOMO part. So highest occupied molecule, so electron-rich. So in addition to that, the presence of ERG, electron-releasing group, enhances the reactivity of diene. Suppose the diene is attached to the electron-releasing group, the reactivity increases. One more point, the diene should be in the cis-side form, that is cis. So it is a single bond cis. So the butadiene, the cis trans isomerism arises due to the carbon-carbon single bond rotation, not for the carbon-carbon double bond. So it is called a S single bond cis. In opposite direction, it is said to be single bond trans. So it must have the S cis conformation. Okay, so cis-side only involves in the DIEL ALDER reaction. Okay, diene can be chain or open chain or the cyclic. So it's an open chain. Some cases it may be cyclic. Cyclic is well and good. It is more reactive than the chain form, and it must have S cis conformation. If dienes are in S trans conformation, the dienophile could not approach both ends of diene at the same time. So the reaction is the concerted, and it is a suprafacial. So if it is in the trans position, the approach of dienophile is not possible. So the diene must be S cis conformation, that is cis-side conformation, and it may be chain or cyclic format, and it should be electron rich, and the reactivity is increased by electron releasing group. Okay. Then here's the question. So among the following, the number of compounds which can participate as diene compound in the Diels order reaction. So this is a question in JAM 2016. So compounds 1, 2, 3, 4, 5, 6, 7, 8 compounds are given. How many compounds are participate in the Diels order reaction? See the compounds. The first one, it is in the cis position, and here it is the cis position. Here also cis positions are there, cis is there, so it will mean what? So compound may be open chain or cyclic. So here the cyclic compounds are here. So it is also a cis position. Here also cis combination. Here see the compound, it is cis or trans. It is in the trans combination. Okay, trans position. And here it is the trans position. It is a cis position. So if you consider this compound, here the oxygen is missing. Here the compound, this one and this one, that is this and this, are in the trans side form. So these compounds not participate in the Diels order reaction as a diene. Whereas other 1, 2, 3, 4, 5, 6. So 6 is the answer. Among the following, the number of compounds which can participate as diene compound is the answer. These two compounds are not involved in the Diels order reaction because it is in the trans side position. Okay. So yes, trans side compound, so does not participate in the Diels order reaction. So number of compounds are 6. Let's move to the next question. So it is the question about diene. Amongst the following, the compound that does not act as a diene in Diels order reaction, we know very well that the cis-side diene is involved in the Diels order reaction. So this is a question from gate 15. What's your answer? The answer is B. Why? And the answer is B. It is a trans side compound. So it is a trans compound. Otherwise, the D and C are the cis compounds. So B does not act as a diene in the Diels order reaction. Okay. Then the nature of the dienophile. So dienophile is a electron poor species. Okay. So some other electron withdrawing groups are present in it. What happens? Automatically it is more reactive. So not only alkenes and alkynes, some other conjugated carbonyl compounds, nitriles, vinyl esters, vinyl ethers also act as a diphenyls in the reaction. So here one more question. So this is a question from JAM 14. Here the malic anhydride is given, compound 5, and what the reactivity of the compound 1 to 4 with malic anhydride is question. So here 1, 2, 3, 4, among the 4, all are in the cis side or trans side. It is a cis side. It is trans side. So in general, we understood that the trans side compounds are not involved in the Diels order reaction, but cis side and trans sides are energy barrier is very, very low. So cis may be converted into trans may be converted into cis. So this open chain trans side, trans compound, trans butadiene also involved in the Diels order reaction by means of giving energy. So one is more reactive. So among the option, B is the answer. So directly the answer is B. Now let's into the explanation. So one is the conjugated diene electron rich, hence it is more reactive. So automatically in the first position among the three. So it is converted into cis-side form. So it is Diels order reaction active. Okay. Then about 3. In about 3, methyl groups are is a electron releasing group, so it increases the reactivity. So it follows the 1. Okay. And what about the tertiary butyl group? Here the tertiary butyl groups are attached, so it is more electron releasing group when compared to the third. But because of the steric factor, it has a less reactive. So it is in the low reactivity case. Okay. So it is a low reactivity in case of 2, and it is a high reactivity. Okay. And compare fourth and third. So third is more reactive due to the presence of electron releasing group. So your order is 2, 4, 3, 1. So what is your answer? Answer is B. Next question. The order of reactivity of the following dienes towards Diels order reaction. So it is a question from December 18. Here the structures A, B and C can be written as. So in case of A, So the tertiary butyl is in the terminal carbon. So it is in the cis form. So we have known that the trans side form can be converted into cis side form at room temperature because the energy barrier is very low, and B and C can be written as. Now in compound A, there is no steric hindrance between the hydrogen and tertiary butyl. In case of C, the two tertiary butyl groups are there. These two tertiary butyl groups keeps this molecule in the trans side form, not in the cis side form. So trans may be converted into cis, but due to the presence of these tertiary butyl group, keep the molecules always in the trans side form. So it has low reactivity. So C is less reactive. So among the options, so A may be. Okay. Then about tertiary butyl, the compound, the B, the second carbon, it has some steric hindrance, tertiary butyl and hydrogen atom. So the energy of this molecule is more. So it is more reactive. So energy increases, reactivity increases. So energy increases, less stable, more reactive. So B is more reactive. So B and then A and C is least reactive groups. Clear? Okay. So the answer is A. Next, there's a question. It is from CSR June 19. Here the correct order of reactivity of the following diene towards reaction with the malic anhydride are given. Two options are given. Two compounds. One is E1-chloro-buta-1,3-diene and E-penta-1,3-diene and E1-methoxy-buta-1,3-diene. So here the various groups are attached. One is chlorine, another one is methyl group, here methoxy groups. So we know about the reactivity. So solve this yourself. Okay. Have you solved the question? If any doubt, please mention in the comment box. So next is the mechanism and stereochemistry of DIEL Alder reaction. So about mechanism. So mechanism is simple. It is one-step reaction, that is concerted reaction with the intermediate cyclic transition state. So cyclic transition consists of 6 members. The simultaneous cyclic movement of 6 electrons. So it is concerted reaction. Yes, cis conformation is a favored structure. Okay, and always it is syn-1,4 addition. Always supraphysical. It is always similar to the syn-1,4 addition with respect to both diene and dienophile. Okay, now the stereochemistry of the adduct. How the stereochemistry of the adduct is predicted with respect to dienophile. So stereochemistry of the adduct due to the stereochemistry of the dienophile. The DIEL Alder reaction is a stereospecific reaction. So if the substituents are in the cis position in the dienophile, then the cis remains in the product. If the dienophile is in the trans position, transform, then the product also trans. So cis dienophile gives cis product, trans dienophile gives trans product in the electron. Regarding diene, stereochemistry of the adduct due to the stereochemistry of the diene. Okay. So in case of diene, there is the outside groups of the diene and the inside groups of the diene. What are outside groups of the diene? What are insides of the group of diene? The outside groups of the diene in the adduct, it is always below the plane of the molecule, and the inside groups always present in the above the plane of the adduct. See what is the outside group and what is the inside group. So this is a typical diene. It is the outside group. The hydrogen is outside group and R is the inside group. Okay. So it is outside and it is inside group. Okay. Outside groups in the adduct always below the plane, and inside groups always it is above the plane. So see this reaction. So butadiene, the two phenyl groups are attached. Here the phenyl is the outside group and hydrogen is the inside group. And it is a dienophile is in the cis position. What is the product we expect? Stereochemistry concept. So cis always gives cis. So there is no doubt. here the outside group and inside group, the positions are. So see the product. In this product, it is the outside group, external group. Here it is in the below the plane. So always below the plane in the 6-member adduct. So it is below the plane. And the hydrogen is the inside group. So it is above the plane. Okay, right. And in the case of dienophile, both are on the cis. So here the adduct also the cis is maintained. Clear? The next part is the endo-exo selectivity. So endo and exo selectivity. So which one is endo and which one is exo? So the concept. So it is a bicyclic compound. So it is a bridge carbon, and there is a cavity. So it is a concave side of the bicyclic ring. Okay. If the group is present in the side, that is cis to the bridge carbon, So here the COOCS is there. It is cis to the bridge carbon. Substitution is pointing away from the cavity, exo, away from the cavity. Okay. Here the group is pointing towards the cavity, So it is called the endo. Otherwise, the bridge carbon and the substituent are in the cis position, then it is exo. If it is in the trans position, it is endo. Otherwise, the group pointing towards the cavity of the bicyclic ring, then it is called endo. Okay. DIEL's order reaction always gives endo product. So because of the steric factor, not in the not exo product. Okay. Substituents is cis to the bridge carbon is exo. Substituents to the bridge carbon is cis is called exo, and the trans is called endo. Okay. Endo product is favorable, and exo products are only formed in the high temperature. So it is kinetically controlled. Endo product is kinetically controlled, and the exo product is thermally controlled. Okay. So at high temperature, exo product due to the conversion of endo to exo. So regarding endo and exo selectivity, in DIEL's order reaction, endo product is always formed. So it is endo rule. See this reaction, subbutadiene and malic anhydride at 25 degrees Celsius, so low temperature. So kinetically controlled product, the combination in bicyclic product is endo to the cavity. And it is heated at 120 degrees Celsius, is converted into exo form. Here the exo is in exo, the malic anhydride portion, diene portion is the exo side. Clear? So these are about the endo and exo selectivity. So regarding this one, the substituents always in the endo side. So you have to remember. So what is endo? So it is the bridge carbon, and in the substituents are in the trans position. Okay. Now orientation effects, that is regioselectivity. Regarding this, if the electron donating group is present in the C2 and C3, so electron donating group enhances the reactivity of the diene. Okay, and the electron donating group is present in the carbon 1 position or in the carbon 2 or 3 position. What is the product? What is the adduct you got? Okay, here the electron donating group in the C2 or in the C3, you get 1,4 adduct. So DIEL's order reaction is the 1,4 addition product we have dealt. Okay, when you get 1,4 adduct, it is the carbon substituent group or the electron donating group is present in the C2 or C3. When the electron donating group is in the C1, you get 1,2 adduct. So this is a orientation effect or a regioselectivity. See in butadiene, the terminal carbon, the electron donating group, releasing group is in the first carbon, C1 carbon. So what is the product you get? 1,2 product. 1,2 product. Okay. 1,2 cycloring substitute products obtained. When it is in the C2 or C3, so now the group is in the C2 position. So it is first, second, third, fourth, C2 position. Now the product will be 1,4, 1, 2, 3, 4. 1,4 adduct is formed. So 1,4 product is formed when C2, C3 in substitution. So this is called regioselectivity of the DIEL's order reaction. So next is very interesting one. that is the intramolecular Diels Alder reaction. When the diene and dienophile parts are in the same compound, so there is a possibility of diene and dienophile part is present in the same compound. Now there may be intramolecular Diels Alder reaction. So here the reaction takes place. You get the plotted cyclic ring. Okay, so this is a product. So it is 1,3,9 deca dry. When electron withdrawing group is not present in the dienophile substance, dienophile does not contain any groups here. Okay, so what is the stereochemistry of the adduct? Here the cyclic ring, the fused carbon. So this is a fused carbon. What is the nature? The dienophilane does not contain any group. So in the adduct, the fused carbon hydrogens are in the trans position. So the hydrogens or atoms are in the trans position. So when dienophile contains any group, so there may be a change in the stereochemistry. The dienophile part has electron withdrawing group in the inner carbon. So dienyl part, the electron withdrawing group is in the inner carbon. See this example, the cyanide group, this electron withdrawing group is present in the inner part of the dienophile part. What is the product you get in the adduct? The fused hydrogen atoms are in the cis position. So both hydrogens are in the cis. When dienophile does not contain any group, the adduct, the fused substituents are in the trans part. Here the fused substituents are in the cis part. When electron withdrawing group is present in the terminal carbon, what is the stereochemistry of the bicyclic adduct? And the geometry is cis. You get both the cis and trans groups. See the example. Here the electron withdrawing group is present in the terminal 1 carbon. And the products are both cis and trans. Here the bridge groups are cis and bridge groups are trans. But the CH2 and hydrogen is in the trans position. It is below the plane and it is above the plane. So the terminal bridge group is always below the plane. Okay, and the bridge groups is trans to each other. Okay, then the geometry is trans. The product is in the different. So what about here? See the group is in the terminal, but it is in the trans position. Here the geometry is cis. The two hydrogen atoms are in the cis. Here the geometry is trans. One is here and one is here. Okay. Now you get the two products, both cis and trans. So it is a trans and it is a cis. And what's the difference? The electron withdrawing group is below the plane, and the bridge is a cis2. Bridge hydrogens are in the cis position. See here the bridge hydrogens are in the trans position, always trans. Okay, the products are cis and trans in both the cases, but the bridge and group is cis to each other. See here it is cis, but here it is trans and it is trans. It is below the plane, above the plane, below the plane, above the plane. So electron withdrawing groups below the plane of the ring and cis to the bridge group. Here the electron withdrawing group below the plane and it is trans to the bridge group. Okay. So that's all about Diels Alder reaction. I think that this is very useful to you. Thank you very much.